Am I audible to all of you?
Yes.
Yes,
Okay,
please go ahead.
okay. So, thank you very much, Abhishek, for the introduction, and thank you, Shine, and all other organizers from ESPOS for giving me this opportunity to deliver a talk on this research work titled Generation of Large-Scale Fast Magnetoacoustic Waves Due to Impulsive Magnetic Reconnection in the Coronal Current Sheet, which I have done in collaboration with Abhishek Srivastav, David Pontin, Eric Priest, Arkwon, and Ting Vion. So before moving on to discuss the scientific findings of this particular work, I would start with some introduction and basic motivation to set the tone of the for the rest of the talk. So whenever we speak about coronal heating, there are two potential mechanisms that have been studied in detail for decades. One is the MHD waves dissipation, which can be due to resonant absorption, phase mixing, etc. On the other hand, magnetic reconnection is another potential mechanism behind the coronal heating. Now, as far as MHD waves are concerned, so they can either be originated at base of the photosphere itself due to the turbulent convection, which then propagate outward in the outer layers of the solar atmosphere. On the other hand, it can also have in situ generation at solar corona itself during the flare, CME, or filament eruptions. On the other hand, when we are trying, we want to talk about magnetic reconnection, first thing that we should have is presence of magnetic discontinuity in our magnetic configuration. Now, this discontinuity can either be finite in the form of quasi-separatrix layers, bald patches, etc., or it can be infinite in the form of magnetic null. Whatever the method of our discontinuity would be, the formation of a current sheet is essential for onset of reconnection. Now, the current sheet formation can be happen when the discontinuity gets collapsed due to either MHD instabilities or some external forcing via shock waves or prominence eruptions. Now, if current sheet has been formed, it can either go to the reconnection phase or it can remain stable for long. Now, when current sheet is remaining stable for long, it again needs some MHD instabilities which can enhance the resistivity locally, and or it can be externally forced via shock waves or other types of processes. So via these processes, it can go to the magnetic reconnection phase. So the MHD waves and reconnections can be studied separately, but here what we are trying to understand that whether this can be these two processes can be connected to each other. So, first of all, whether there are some numerical studies which study the interaction of waves with magnetic nulls. So, as you can see here, there are lots of references or in literature where they have studied this in numerical simulations. Whether it is only limited to numerical simulation, exactly not. Rather, we have some observational motivations in certain papers. On the other hand, can waves can be generated due to flare or reconnection? Yes, again, numerical studies are there, and then observational motivations are also there. So with this introduction and motivation, now our aim is to find out whether these two scenarios can be achieved in one particular simulation, and moreover, can we observe both this scenario in solar corona in connection to one another at the same region of interest. So which we called as symbiosis of waves and reconnection, which means that waves and reconnection are happening in contention to each other, in expense of each other. That's why we termed it as symbiosis. Now, let us move on to have a quick look at the numerical setup which we have. So, since our area of concern is the solar corona, so we took density and temperature in such a way that it mimics the typical coronal condition. When we have the magnetic field, so in case of magnetic field, it has a overlying horizontal field line, and then it has a magnetic dipole which is exactly opposite to the overlying field line, so that it can generate a magnetic null point at certain height, which is at the center of our simulation box. So this magnetic field is basically potential in nature. So in presence of uniform density, temperature, and this potential magnetic field, our initial condition basically poses a magnetohydrostatic equilibrium. Now, since we are trying to understand the magnetic reconnection process, so we consider a magnetic diffusivity of 2.4 into 10 to the power 8 meter square second inverse. Now, to perturb our initial equilibrium setup, we perturb it with a velocity perturbation, which is Gaussian in nature. And here are the parameters for this Gaussian perturbation. But if you look at this V naught value, which is 850 kilometer per second, it it shows that it should be very higher as far as corona is concerned. So I will come to this point in a later slide why I have taken this much higher value. Also, since viscosity can have two effects such that it can limit the motion of the plasmoids and eventually that can limit the coalescence process. On the other hand, it can also dissipate the waves generated in our simulation. So we have considered the viscosity also. Now, with all this initial condition, we basically solved this set of MST equations to simulate the entire dynamics. Here are some normalization factors such as L star, rho star, which has been used to normalize the physical variables such that they can be computed via a computer. So, therefore, since in our simulation we are achieving the coalescence instability, which basically connects the smaller length scale within the plasmoids. So therefore, we need a higher resolution in our simulation. So after 5 AMR levels, the resolution reaches at 48 kilometer. Now, to have temporal integration and estimation of flux at cell interfaces, we have basically used the two-step RK method and HLL solver in our simulation. As far as boundary conditions are concerned, we have considered the continuous boundary conditions to ensure zero gradients for all the physical variables across all the boundaries. So if you look at this animation here, it shows that there is a Gaussian perturbation which basically interacts with a magnetic null at x equals to 0 and y equal to 102 megameter. It basically collapses the magnetic null point to form a current sheet uh, in the direction of x direction. So to understand what role the wave is playing here, so okay, so first question is why I have taken the higher amplitude of wave. So if you see at 0 second, the normalized value of the amplitude of wave is around 7, which corresponds to 850 kilometer per second is the physical value. But as you can see, as the wave is propagating towards the current, towards the magnetic null, which I have shown here as the vertical dotted line, so it basically diminished its amplitude with time as it propagates in the space. Also, you can see here is a sawtooth profile forming, which basically manifests a shock formation, which is due to the fact that the wave is coming from a higher Alpine speed region to a lower Alpine speed profile. So the leading edge is getting a lower velocity than the trailing edge, which forms a shock. So the shock, when it is interacting with the null point, it has a amplitude of the order of it has an amplitude of 60 kilometer per second, which is reported in solar corona. Now, the next question is what roles the wave is basically playing here. So, as I shown earlier, that the wave is reaching the magnetic null at time 108 second. Now, you can see here that at 0 second and 96 second, the inflow magnetic field, which in our case is Bx, are similar to each other. Therefore, there is no perturbation in the inflow magnetic field across the magnetic null point. But at 108 at 120 just after the interaction of wave with the null point, you can see the inflow magnetic fields are perturbed by certain amount. So fair enough. Now wave is basically playing its role to perturb the magnetic field across the null point. Now what the perturbation in the magnetic field is doing in initiating the reconnection. So you can see here the red arrows which corresponds to Lorentz forces. You can see the perturbation in the magnetic field is such that the Lorentz forces are acting towards the magnetic null point to collapse it in the x direction, forming a horizontal current sheet here. So this is the part what wave can do to initiate the reconnection. Now the other way around is in the later stage, we can see once the current sheet has been formed, it eventually gets elongated in the x direction and thinned down in the y direction. As the aspect ratio is such that it has been uh, more than the threshold of plasmoid instability, the plasmoids are getting formed and eventually they get coalesced with each other. So during the motion of the plasmoid as well as the coalescence of the plasmoid, it is forming the rippling wave fronts there. Now from this simulation, you can see you can have two queries. One is some of the plasmoids are moving without getting coalesced, and once you can see the waves are predominantly moving in the upward direction, not in the downward direction. So you have to understand why some plasmoids are getting coalesced, the others are not, and why all of the waves have been realized in the upper part only. So first of all, if you look at these arrows which are black, so here you can see the black arrows within two plasmoids are changing its orientation rapidly. It means that the Lorentz force is changing its orientation, which means it is somewhere attracting the plasmoids to merge, and then there is a repelling force which is stopping the merging. So therefore, this is a tug of war between the attraction due to the parallel current within the two plasmoids and then the repelling force due to the reconnection outflow or magnetic tension is opposing the merging. So when the attraction force overcomes the repelling force, then only the plasmoid coalescence will take place. Then the next question is, do waves propagate only upward from the current sheet? Now if you see the top left panel, you can see the perturbations are in both the direction in the velocity, but it can hardly seen in the density perturbation or even in the current density or even in the total pressure. So naturally the question arises, uh, even though we have velocity perturbation in both the direction, why don't we see or why don't we realize the presence of wave in the bottom part of the current sheet? So here is the answer. So if you look, the background density is considerably lower in the bottom part of the current sheet. Also, the background magnetic field strength is much higher in the bottom part of the current sheet. These two conditions basically result in a higher alveolar speed, which further result in higher phase speed. So according to Liu et al., the maximum perturbation in density due to fast mode waves can be del rho max rho del V by VPH. Now consider that del V is similar in bottom as well as upper part, but since rho is lower in the bottom part and VPH is higher in the bottom part, which means the del rho max will be very lesser in the bottom part in comparison to the upper part. There that's why we don't see any wave like perturbation in density as well as in the current density due to the higher magnetic field also, and we only can see the perturbation in velocity. So then we focus only on the waves which are propagating upward from the current sheet for the rest of the analysis. So here first question is whether this ripple like large scale wave fronts are uh, fast mode magnetoacoustic waves in reality. So to check that, we have two conditions here. So if you look at this equation on top left, it shows that if omega by k, which is the phase speed, if that is greater than Vs cos theta, where Vs is the sound speed and theta is the angle between the angle of the propagation and the magnetic field vector. So if for fast wave omega by k is certainly greater than Vs cos theta, therefore this B naught dot B by mu naught should be in phase with the P. Therefore, magnetic and plasma pressure perturbations associated with waves should be in phase for fast wave. The second thing is the propagation speed of this wave should be consistent with fast mode phase speed. So to check or examine these two conditions, what we have done is we have taken three slits in three different orientation. Let's say S1, S2 and S3. Also we have taken three different locations along these three slits, that is 1, 2 and 3. Now we have extracted the time distance diagram along this slit S1, S2 and S3, which shows that there is outward propagating wave fronts in the form of tilted ridges in this uh, time distance diagrams, and we see that the propagation speeds are coming to be around 500 km per second. More importantly, if you look at the bottom panel here, where the top bottom panel is basically the total changes in the thermal pressure and magnetic pressure, and then we do the detrending to subtract the background trend to find out the small scale fluctuations associated with waves. So as you can see from the bottom panel, the small scale fluctuations in thermal pressure and magnetic pressure are in phase in all of these three locations, which confirms that the waves are moving in a fast mode manner. Then we calculate the periodicities of wave in this location 1, 2 and 3. To do that, we again subtract the background trend in the density to find out the perturbation in density associated with waves, and then use the uh, wavelet estimation to find out the periodicities, and we find out that the periodicities are coming to be 59 second, 70 second and 91 second. Now during this all of this detrending, we consider the box cut average width to be 7 or 8 in these locations, such that the detrended light curves are going through Gaussian with peaks and dips. So now since the background is itself changing with time, also from A1 and A2 uh, we can get a signature that the magnetic fields, which are these magenta lines, are changing their orientation with time also. So the background parameters are changing, or and the magnetic fields are changing in orientation also. So therefore we have to calculate the first mode's phase speed at location 1, 2 and 3 at each time using the instantaneous values. So first of all, the angle subtended by magnetic field vector with positive x direction has been calculated using phi equals to tan inverse by bx, and therefore we consider that at location 1, 2 and 3 the waves are basically moving along the direction of S1, S2 and S3 slit respectively. Therefore, the angles subtended by these three slits with positive x direction are 135, 90 and 45 degree. Then angles between propagation direction and background magnetic field at location 1, 2 and 3 at instantaneous time are calculated using 135 minus phi at estimated at location 1, 90 minus phi estimated at location 2 and 45 minus phi estimated at location 3. Therefore, finally, we calculate the first mode characteristic speed with this empirical formula as provided by Holloway 1975 using the instantaneous values of Cs, Va and theta kV to find out the first mode characteristic speed at each time. So here are few figures which shows how the inclination angle phi changes with time at location 1, 2 and 3. So as you can see at location 1 and location 3, the inclination angles are basically changing from -3 to 2 or 3 to -2 respectively. Whereas in location 2, which is vertical to the which is almost perpendicular to the almost horizontal magnetic field lines, Therefore, the inclination angle there is very small, uh, which is of the order of zero point 0.1. Using this inclination angles and using the formula that I have shown in the previous slide, the phase speeds are calculated to be within 400 to 600 kilometer per second. Here, the red curve is basically showing the phase speed which we have calculated from the formula I have shown in the previous slide. Whereas the solid black curve is showing the phase speed if we consider that theta is 90 degree. So therefore, at location 2, since theta is almost 90 degree, so therefore the solid red curve or solid black curves are overlapping with each other. So now it's clear that we have a fast wave which is propagating to larger distances. Now the basic thing is how much wave energy it is transporting to the longer distances. So to do that, we calculate the wave energy density using this formula, which has this rho by 2 vx square plus vy square and then plus bx square plus vy square by 8 pi. The first term on right hand side is basically the kinetic counterpart associated with the wave, kinetic counterpart of perturbation associated with the wave, and the second is the magnetic counterpart. Now here this px, py, bx, by are basically the perturbations in velocity and magnetic field. To, to calculate this perturbations, what we have done, again we have detrained the background trends and then find the fluctuations associated with in these particular variables. So we use this formula to calculate the wave energy density. Now, since we have multiple sources in our simulation, we can't rely on plasmoid coalescence events periodicity to find out whether it is similar to the periodicity of wave. Rather, what we have done, we have taken 5 specific events here, and then we consider that for each event, we track the center of the coiled plasmoid. For example, this E1, E2, E3, E4, E5, we have 5 events. So we have considered how the coiled plasmoid is moving with time and then calculate the distance between the instantaneous position of plasmoid to the location 1, 2, and 3, and then consider a average propagation speed of 500 km per second to find out the rough wave arrival time if it is getting generated due to certain events. So therefore, if you look at these bottom panels, the shaded regions are showing those wave arrival times for this 5 different plasmoid events. Now, these shaded regions are well correlated with the wave energy density peaks here, which tells us that the perturbation at a higher height or larger distance from the sources in wave energy density is well correlated with different specific plasmoid coalescence events. So this establishes the spatio-temporal correlation between multiple coalescence events and wave energy density peaks. So since we have wave energy density and also the phase speed, we calculate the wave energy flux using this formula, and then we see that the wave energy flux are coming to be order of 10 to the power 5 arc semi minus 2 second inverse. Now the question is whether it is sufficient for coronal heating or driving solar wind. So according to Withrow and Noyes, if quiet corona is losing its energy due to radiation, thermal conduction, and solar wind, the total energy loss will be 10 to the power 5 arc semi minus 2 second inverse. Also, in coronal hole, the total energy loss should be radiation and due to radiation and thermal conduction should be 7 into 10 to the power 4 arc semi minus 2 second inverse. In addition, the energy needed to drive solar winds in active region can be less than 10 to the power 5 arc semi minus 2 second inverse. So therefore, using all of these points, we can confirm that what the energy transport by our wave to largest distance of 60 megameter from the source region is sufficient enough for heating quite coronal holes when they are subjected to energy loss via radiation, thermal conduction, or solar wind. And also, it is sufficient to drive solar winds in active regions. So, now, since we have viscosity, thermal conduction in our simulation, and also the wave has sufficient energy to hit the solar corona if it gets dissipated. Now, due to the presence of viscosity and thermal conduction, do we really see any signature of dissipation here in the present simulation? So, the answer is no. But why? So, the reason lies in these points which has been put forward in Porter et al. So they said that wave energy decay rate is independent of the B naught, which is the background magnetic field, if we consider the damping due to viscosity, whereas it varies as 1 by B naught square for damping associated to thermal conduction. They have also calculated that wave energy decay rate should decrease by only 1.5 to 4 times when V naught has been increased by 10 times. So therefore, uh, it is not decreasing by very higher value. In addition, they reported that damping length of a fast wave of 10-second periodicity while propagating at 45 degrees should be 130 megameter when the background number density is 10 to the power 9 semi minus 3, background temperature is 2 into 10 to the power 6 Kelvin, and P naught is 10 Gauss. More importantly, wave energy decay rate has been reported to vary as T to the power alpha tau to the power minus 2, where alpha ranges from 2.5 to 3.5, and T is the background temperature, tau is the periodicity associated with wave. Now, with all these points in mind, if we look at in our simulation, we see that V naught increases as Y increases. So if you go farther away from the source region, B naught is basically increasing. Also, at a particular height or particular distance from the source, B naught is only varying between 7 to 9 Gauss, which is not higher variation. So therefore, uh, and also we have higher periodicities of 60, 70, and 90 second associated with the waves generated in our simulation. So with all these points, we can conclude that according to 1, 2, and A, decay rate will not vary significantly due to magnetic field strength. According to 3, 4, and B, decay rate will be much smaller for waves generated here. Hence, damping length will be much higher than 130 megameter, so which is higher than our simulated spatial domain. So due to these reasons, we do not see any signature of dissipation of waves in our simulation domain. So here are the key takeaways. So interaction of shock wave like perturbation with magnetic null results in null collapse and formation of current sheet. Then current sheet elongates in length and thins down in width to reach beyond the threshold of aspect ratio, which is required for onset of plasmoid instability. Therefore, plasmoids can undergo merging with each other at various separate events to form bigger plasmoids. During these plasmoids or even during the motion of plasmoids, they are associated with generation of ripple-like large-scale wavefronts. Then what we have done is we find out that there is an inverse relation between thermal and magnetic pressure. Also, the propagation speed is consistent with the measured fast mode speed. Uh, these two confirmation basically suggest that the waves that are generated in our simulation are basically fast mode in nature. Also, the periodicities are found to be 60, 70, and 90 second at three locations of measurements. Then we have shown that peaks in wave energy densities are well spatio-temporally correlated with specific plasmoid coalescence events. Wave energy fluxes are sufficient for driving solar wind in active regions, heating in coronal holes and quiet sun if it gets dissipated via some means. However, we do not see any wave dissipation in present simulation. So most importantly, this simulation is acting as an important example of the scientific idea that namely symbiosis of waves and reconnection. But we argue for more focused observation on this proposed line to support this interesting scenario which we have studied in our simulation. So, finally, thank you.